Hello, this is Mr. Craig, and I wish to go over the answers for the second semester Honors Chemistry Final Exam Review. Let's get started. Question number 1 says, name the three bond types and describe the differences between the three. Now, I'll admit I wasn't very clear on indicating what type of bonds I was looking for, but this one is actually asking about the types between atoms. If we were talking about the types between molecules, there's other ones. We can talk about that as well. But let's talk about what I have here in the answer. So, nonpolar covalent, polar covalent, and ionic. And when we talk about covalent, hopefully you remember the one word when you hear that's associated with the word covalent. And hopefully you're thinking about sharing. So when we talk about nonpolar covalent, what that means is that we have equal sharing of the electrons between two atoms. A polar covalent bond deals with the unequal sharing of electrons. And we know that they're unequal because the atoms have different electronegative values, and so the higher the electronegative value, the greater the attraction for the other atom's electrons. And you'll get an electronegativity sheet, and fluorine actually has the highest and francium has the lowest. And again, what that translates into is that francium doesn't want anybody's electrons, and it's actually in the business of trying to get rid of it, where fluorine wants to have electrons. Now you may ask, well, why are there no electronegative values associated with noble gases? It's a good question. Noble gases already have their 8 valence electrons. They're not interested in getting any. However, if we get lower on the periodic table, as we'll discuss in AP, that things like krypton, xenon, radon do make some molecules because they're so large, and that some atoms can steal and share some of those electrons. Not necessarily steal, but sort of borrow, so to speak. So, and then the other type is the type of bond that you have between a metal and a nonmetal, and that's called an ionic bond. So these three different types of forces actually exist between atoms. Now, if I were asking about the types that we have in between molecules, we call those intermolecular forces, or IMFs. And the three different types that we have there, or not three, but we have different types. We have the dispersion, we have dipole-dipole, and we have hydrogen bonding. And the criteria for that is actually knowing if you have a polar or nonpolar molecule. And I can't remember if we have a question like this later on, but it's a good time to talk about it. Dispersion forces are those forces between molecules for only nonpolar compounds. Now, when you're talking about a polar and a nonpolar compound, you have to draw the Lewis structure out. So I'm trying to remember if I have, I do. I have a structure here, and this is actually an octahedral shape. And I'll try to get it a little closer to the computer. But you'll notice that all the external atoms there are the same. And there's no lone pairs on that central atom. So if you had a situation like that, this actually exhibits a nonpolar molecule, or it is a nonpolar molecule, which has dispersion forces. However, if we take off one of those atoms and we have a lone pair now what that means is that we have a polar compound. And so now it falls under the criteria, do we have a dipole-dipole or a hydrogen bond? Well, if there's no hydrogen on this molecule, yet it's polar, then we have dipole-dipole. If there is a hydrogen, then we got to look at one other thing, and that's actually, is that hydrogen that is attached to this molecule, is it bonded to either a nitrogen, an oxygen, or fluorine atom? Now again, these are within the molecule, and I know it's kind of wacky to be thinking about that. But again, that does allow for the stronger hydrogen bonding, which causes for higher boiling points, higher melting points, and stronger surface tension. So again, the types of bonds, it's kind of nice to know what type of bonding you have between molecules, because it does give it its characteristics associated with that. All right, let's look at number 2. And number 2 asks, the difference in electronegativity determines whether a bond is covalent whether it is a bond is covalent. So again, these are general trends that if you have, say, darn it. Let's say that we have, sorry, I'm trying to get my colors here. If you have a difference of 1.7 or higher between atoms, differences in electronegative values, then you're looking at an ionic bond, which is the stronger of these three types that we're talking about here. if the difference in electronegativity is generally between 0.1 and 1.7, and you do not have a metal bound to a nonmetal, then we say that that's a covalent bond. And then if we have the 0, then that means that we have a nonpolar covalent bond. So again, these are some good general rules, but sometimes we can actually violate that if we're looking at a metal that has kind of a high electronegative value and a nonmetal that has a lower one. The difference would fall between 1.7 and 0.1, but again, if you have a metal with a nonmetal, we're going to make that an ionic substance. All right, number 3. Number 3 says name physical properties each associated with all the 3 bond types. Kind of talked about that already. I'm not going to ask you a question about physical properties. It just deals with how well something, at the temperature which something boils at, something melts at. So those are physical properties, things that we can look at from afar and visually observe and see what's happening. So if you're looking at, say, something that has strong intermolecular forces, then it has a high boiling point. If it has weak intermolecular forces, it's probably a gas at room temperature. That's what I'm looking for on that question. Number 4. Which element of the pairs has the largest ionic radii? And the first one is between sodium and oxygen. Let me pull up a periodic table here. Okay, so here's our periodic table. And the question is asking who has a larger ionic radii? Now again, remember what ionic means is that it's something that has a different number of electrons from that which it started. So if it's sodium, sodium's over here, and sodium actually has 11 protons and 11 electrons. But when sodium turns into an ion, does it gain electrons or lose electrons? What do metals do? Do they gain or lose? That's right, they lose. So it'll change that 11 to a 10. So it'll have the same number of valence electrons. In other words, it'll lose its 1 electron. And it'll have 10 total electrons, but 11 protons. Oxygen, on the other hand, oxygen has 8 valence electrons. I'm sorry, 6 valence electrons, but a total of 8 protons and 8 electrons. And when it turns into an ion, it'll gain 2 electrons and have the same number of electrons as neon. So here's the question. We have oxygen with 10 electrons, sodium with 10 electrons. Who is bigger? Well, oxygen has a -2 charge, sodium has a +1 charge. Sodium has 11 protons, where oxygen has 8 protons. Therefore, if you have more electrons than protons, your orbitals are going to not be able to satisfy, or they're going to get larger because your protons aren't able to pull in those electrons. So the more negative it is, and we have the same type of number of electrons, what that means is that we have a larger radius. Sodium actually has the smaller of the 2 radii in that case. The next question asks, who has the larger radii between nitrogen and antimony? Well, let's take a look at the periodic table. Nitrogen's right here, antimony's right here. They're in the same column. They both have the same number of valence electrons. In this case, it's all about the total number of orbitals. Well, nitrogen only has 1s, 2s, 2p orbitals, where antimony has all these d orbitals, all the p orbitals. It's in the 5th energy level. Antimony, in this case, is going to be larger, even though they both have the same charge of -3. So in that case, because antimony has more orbitals to start off with, it's going to have a larger ionic radius. All right, let's take a look at the next one. Bigger ionic radius between calcium and zinc. Okay. Well, looking at zinc, which is right here, and calcium, which is right here, they both are going to have a -2 charge. So knowing that they're both going to have the same charge associated with it, they're both going to lose 2 electrons. However, they're in the same energy level. They're in the 4th energy level over here. Which one would you suspect would have a larger ionic radius? They're both going to have the same charge. Well, if calcium loses 2 electrons, How many total electrons will it have? Very good. It'll have 18. It'll be the same number of electrons as argon. If zinc loses 2 electrons, then it will only have 28 electrons. But it still has all these d orbitals and s orbitals that have electrons in it. So in that case, even though the charges are the same, they're both in the same technical row, not in the same energy level, calcium in this case will have the smaller ionic radius, where nickel has the larger. All right, number 5, draw the Lewis structure for the following. Hopefully we are okay with drawing Lewis structures. Again, my suggestion when doing this, find out how many total valence electrons each brings. So hydrogen brings 1 electron, nitrogen brings 5 electrons, oxygen brings 6 electrons, and there's 3 of those. The -1 actually means that we have 1 more electron added to this. Oh, I'm sorry. Sorry. This is only that guy there. So what that means is we have 18 plus 6, so really we have 24 valence electrons for this structure here. Now, what may have not been so obvious is that this was ionic. And again, I wouldn't do this type of structure to you because that's more of an AP concept, but it's still okay. Hydrogen is actually going to give its electron to the nitrate, and there's a visual representation why nitrate actually has a -1 charge, because the electron that hydrogen had was given to somebody over here so that everybody could have 8 electrons. However, the other 2 shapes, the carbon dioxide and the aluminum trifluoride, I would expect you to be able to do Lewis structures for. And again, make sure you're doing the difference in the electronegativities first to find out what type of bond you actually have between the atoms before you actually draw out the Lewis structure. So when doing the difference in electronegativities, you'll find out that we have a polar covalent bond here, whereas we have ionic here. What that means is aluminum, which brings 3 valence electrons, is giving 1 electron to each fluorine, so that fluorine, who brought 7, now has 8. Where over here with the carbon dioxide, the carbon and the oxygen atoms are trying to get 8 electrons. That's why we see double bonds here, plus the lone electrons here. Okay, so again, you're going to be asked about Lewis structures. I will only ask on the test Vesper shapes for things that are sharing electrons. I won't ask about shapes like this. So no ionics will be in Vesper. So you should be able to tell me the Vesper shape for this. And if it's polar or nonpolar. What is the shape? Very good. Linear. Is that polar or nonpolar? That is absolutely nonpolar. So how do you know it's nonpolar? Well, it's symmetrical. How do you know it's symmetrical? Because we have oxygens out here. All the external atoms are the same. And you'll notice carbon has no lone pairs. Therefore, it's a nonpolar compound. If I had, say, a sulfur here instead of an oxygen, now we have a polar compound because we have different external atoms. All right, next question. Determine the molecular shape for the following. So this is a Vesper question. I would want you to draw out what these look like. So water looks like this. So if I were asking you what is the shape, my potential for this shape is 4. I have 1, 2, 3, 4. So looking down the column for 4, at the top is tetrahedral. Go 2 more down, I have a bent shape. Ionic, I'm not going to ask you about shapes. Okay, so I'm going to ignore B and E. But do realize that they are ionic and that we don't do anything with Vesper for that. Okay. Looking at Sf6 Sulfur Hexafluoride, and yes, we are violating the octet rule, so we have fluorines all around here. And if you give all the fluorines their 8 electrons, yes, there would be more than 8 electrons on the sulfur. There actually would be 12 in this case. And the reason why sulfur can have more than 8 electrons or violate the octet rule is because S has access to the d orbitals. It's in row or the 3rd energy level, 3rd row or below. And then xenon tetrafluoride. So xenon looks like this, where we have fluorine here, fluorine there. And then when you count up your electrons, we have extra pairs, that 2 pairs that are not actually forming a bond with anything. Now again, when looking at these shapes, the potential for this is I have 4 atoms of fluorine plus 2 lone pairs. That gives me a potential of 6. The first name that's in that column of 6, octahedral. Go 2 more down because I have 2 lone pairs. This is a square planar. Follow-up question, is this polar or nonpolar? As a molecule, is this a polar or nonpolar molecule? And I have the shape right here. So I'll let you take a look at that. So if you take a look at that, is that polar or nonpolar? Okay. What kind of shape is that? Square planar. So that is one of your exceptions to the rule where you have lone pairs and it's a nonpolar compound. Number 7. Describe how a polar covalent bond is created. Number 1, covalent means that we're sharing. Polar covalent means that it's unequal sharing. So how this takes place, let's say that we have something like hydrogen and fluorine, and we're sharing those 2 electrons between the 2. Okay? The way that a polar covalent bond occurs is that fluorine brings 1 electron to share, hydrogen brings its 1 electron to share. But what's happening here is that since fluorine has an electronegative value of 4.0 and hydrogen's 2.1, these 2 electrons are actually a little closer to the fluorine, than they are the hydrogen. So since those electrons are actually a little closer, we have what's called a partial positive charge. Partial negative charge on the fluorine, where the partial positive is on the hydrogen. So it's kind of like I'm sharing this 1 electron with somebody. However, that electron that I brought with me is closer to the other individual than it is to me. I can still feel that electron a little bit, but it's not a full-blown positive charge, as if I gave it to somebody and said, I no longer have it, and I lost an electron, now I have a positive charge. However, since I still have an attachment to it, because I'm sharing, I can still feel a little bit of that negative charge, but it's not a full-blown negative charge. And when that electron gets closer to the fluorine, it's like, oh yeah, hydrogen, you just gave me that electron. Oh, that electron's so much closer to me, I can feel more of that negative charge than you can. That's why we say it's a partial negative charge on the fluorine. All right, number 8. Determine if the following molecules are either polar or nonpolar. All right, oxygen. Well, oxygen looks like this. So all the external atoms are the same. There's no unequal sharing of electrons. That's a nonpolar compound. Calcium chloride is an ionic compound. All ionic compounds are polar. Period. They're all polar, so don't even argue with that. Water. Again, just had it drawn up here a second ago. This actually has a bent shape. It's not linear. It's a bent shape. So the reality of this looks like this. Okay, where that bent shape, okay, is not going to cause the 2 atoms to tug away from each other or form a nonpolar compound. C3H8 or propane. So we have all of our carbons in a row here. Oh, sorry. We have all of our carbons in a row here. Now, we do have nonpolar covalent bonding between the carbons, but we're not going to look into that. Here we have our hydrogens. All the external atoms on those hydrogens are the same. So what that means is, since all the external atoms are the same, no lone pairs on the central atom. There are no lone pairs. All carbon always has 4 bonds, or it's not a happy carbon. And so in that case, that's a nonpolar compound, which means it has symmetrical, a symmetrical shape associated with it. Ethanol, CH3OH, looks a little different, where it has the carbon, the oxygen, and the hydrogen, and then we have our hydrogens here and here. So hopefully you can look at that and say, well, if I'm saying the atoms that are attached to the oxygen or to the carbon are the same, they're not. So that right there makes it a polar compound. But what makes it even more special is we have that oxygen that is bound to a hydrogen in a polar compound. So this right here gives us hydrogen bonding. But still, it's a polar compound. Number 9. Rank the following intermolecular forces in order of strength from weakest to strongest. Again, intermolecular means it's between molecules. Intra means between atoms, so we're not asking about that. But dispersion is the weakest. And then, again, because that's what nonpolar with nonpolar compounds. Dipole, that's polar, but it's weaker than hydrogen bonding, again, with a polar compound. But the strongest of all of them, ionic. And again, a lot of the ionic compounds are solids at room temperature. And we'll talk about here in a second that the strength of the intermolecular forces determine if it's a solid, liquid, or gas. Most things, not all, most things that have dispersion forces are gases at room temperature. These are typically liquids at room temperature, and the ionic is typically solids at room temperature. All right, rank the following in order of increasing boiling point. Again, the stronger the intermolecular forces will determine who has the higher boiling point. Sadly, we didn't go into that. In AP we do, but we're not going to talk about it here. Okay? Sorry about that. Sorry for putting that question on there. Getting into the gases, number 13. What creates pressure? Gases, there's a lot of things that can create pressure. So if I have a fixed volume, let's say that here's my old Diet Coke container here. If I have nothing in here but gas, and I start to heat the surroundings, this is actually going to get very, very pressurized because the gas that's in here is moving very, very quickly. So that's one thing that can increase the pressure. By increasing the temperature, you cause that the number of collisions on the surface of the container increases. If I have that same container and I add more gases to it, the pressure is going to increase. If I were to take this bottle and twist it in such a way that the volume gets smaller, that will increase the pressure of a gas. So there's a lot of things that we can do to change the pressure or to cause gas pressure to increase. Okay, so what causes pressure? Gases. What is an elastic collision? An elastic collision is the type of collision that gas particles have. They don't stick together when they collide. In other words, like you'll see a lot of things that when they collide, they kind of stop because their energy is in such a way where they can't bounce off of each other. Gas particles, they hit, the energy that's transferred is equal, and it's considered an elastic collision. That's why gas particles are constantly moving. The thing that changes that is temperature. Whenever you're working with gases, always convert your temperature to kelvins. Okay? Always have your temperature in Kelvin when working with gases. So make sure you can do that. You're either taking degrees Celsius and adding 273, or if I gave you Kelvin and I wanted to find out how many degrees Celsius, you subtract 273. Number 3, define the 3 normal states of matter in terms of volume and shape. Gases, these are things that are moving around constantly. The shape and the volume are related to the container that it's actually within. Okay. Liquids, the volume is consistent. In other words, I have my Diet Coke here. You'll notice that the liquid doesn't just jump up on its own, but if I turn the container, and I left it like that, the volume of that liquid would stay consistent. So it doesn't change by a lot. If it's a solid, well, the only way that that's going to change is if I crush it, or if I heat it up, or if I react it. So solids are a lot more stable than, say, gases or liquids. Define a crystal. A crystal is anything that's a solid. It has a regular pattern, a regular arrangement. It can be ionic. It can be just made up of only metals, but it has a structure associated with it. So I have on here, it's a regular, consistent pattern that remains unchanged as long as the temperature remains the same. Or if there's no external pressure that's really like causing it to change. And again, it has to be a force that causes it to change in that regard. Number 18, what is an amorphous solid? An amorphous solid is a solid that has no pattern, no arrangement, no regularity to it. Glass is a great example. It is a fluid. It's a very, very slow-moving fluid, but it doesn't have any crystalline structure or lattice structure, which you might hear that term when you get into AP. Number 19, what is the relationship between the strength of an intermolecular force and of the substance? So again, I have on here boiling point and melting point. The stronger the intermolecular forces, the higher the boiling point, the higher the melting point for that substance. If you're looking at vapor pressure again was back when we talked about gases, and I could get water to boil at room temperature because I removed the atmospheric pressure. I lowered the atmospheric pressure enough so that the water molecules could actually change from a liquid to a gas on its own. So vapor pressure is the amount of gas that's above a liquid when it's evaporating. And the stronger the intermolecular forces, the lower the vapor pressure that's associated with that. Evaporation rate, kind of the same thing as vapor pressure. Evaporation, if I left a beaker of water out on the table at room temperature, it would take a while for it to evaporate. If I left a beaker of acetone, it wouldn't take very long for that to evaporate because the intermolecular forces are so much weaker. So evaporation rate is due to the speed in which the liquid changes into a gas. Now, if I increase the temperature, then I'm weakening the intermolecular forces. So that being said, there has to be some variables of consistency when we talk about evaporation rate and vapor pressure. Volatility, that's the ability, so volatility, again, that's the ability for a liquid to change into a gas easily at room temperature. Things like acetone, alcohols. In other words, when you put alcohol on your arm, or when the nurse puts alcohol on your arm for a blood draw or something like that before a shot, it feels cold because the alcohol is reacting with the heat in your skin and evaporating quickly, which draws the heat out. And again, alcohols are very volatile. Doesn't mean that they're all explosive, but a lot of them are flammable. Surface tension, I had a video where I took a paper clip, put it on water, and then took a dab of soap, a really small amount of soap, put it in the water, and that paper clip fell to the bottom of the beaker because the surface tension had been weakened. But surface tension is associated with the strength of intermolecular forces as well. So if you increase the intermolecular forces of a liquid, then it can support or have a skin, so to speak, when we talk about surface tension. All right, what is sublimation? Sublimation means that we are actually going from a solid directly to a gas without going through the liquid phase. So that's what sublimation is. And you'll need to know all those phase changes. And there's 6 of them. And I'll show you all 6 of them here in a moment. Number 21, at the boiling point of a liquid, the vapor pressure is equal to the atmospheric pressure. And I spoke about that earlier in the year, that if you're boiling water, you're at home and you're cooking, and you notice that the water's starting to boil, you'll see steam above that water. Now, the reason why you see the water boiling is because the vapor pressure, which has been created because the water absorbed all that energy or heat, is causing those particles to move at such a quick rate that it's easily able to change from a liquid to a gas to form that vapor. So when the vapor pressure is equal to the atmospheric pressure, when you're boiling water, there's a lot of liquid that's changing into a gas, then you'll see something boiling. 22, the boiling point of water will be less at higher altitudes than at lower altitudes. And kind of think of it like a swimming pool. So if you have your swimming pool, the pressure at the top of the swimming pool isn't as great as if you went down, or if you were at the bottom of the pool here, okay? You have all that water pushing down on you. Same thing with air. Air is attracted to the earth due to gravity as well. That's why all the air doesn't just leave, because it is held to the earth by gravity. And at the closer to the surface, we have more air molecules than we do up at the upper part of the atmosphere. So you lower the atmospheric pressure, you reduce the number of gas particles, then things boil more easily because there's not all that external pressure pushing down on the liquid to help prevent it from changing from a liquid to a gas. All right, in a phase diagram, the triple point is where, and actually I'll just point to the triple point right here. So right here is your triple point. And notice along this table here, you have your pressure and your temperature. Okay, so at some given temperature and pressure, depending on where your data falls, okay, will give you a triple point. And at the triple point, that's where your substance can exist as either a solid, liquid, or gas at that temperature. Now, everything has a triple point. I believe water is like 0.4 degrees Celsius, but it's really hard to get water at that temperature, and I can't remember what the pressure is for, but that when we're talking about the pressure, we're talking about the atmospheric pressure. So I know the temperature is around 0.4, but I can't remember what the actual pressure is that's due to that. Number 24, the boundary lines on a phase diagram represents the phase change. So in this area right here, and right here, and right there, that represents the change. So going from either from a solid to a liquid, or a liquid to a gas, or a solid to a gas, or a gas to a solid, or a liquid to a solid, or a gas to a liquid. And make sure you know all those names that I just rattled off there. So again, going from a solid to a liquid, you're melting. Going from a liquid to a solid, you're freezing. Going from a liquid to a gas, you're evaporating or vaporizing. And then going in the opposite direction, gas to a liquid, condensation. Down here looking at solid and gases, going from a solid to a gas, we just spoke about it, sublimation. Going from a gas to a solid, that is deposition. Okay. Critical point, we don't really speak a whole lot about, but what that means is that the critical point, no matter what pressure you apply to the gas, it has so much energy that you cannot compress it back into a liquid. Normally, we can, for a lot of gases at a lot of temperatures, we can compress a gas so much that it actually changes into a liquid as long as we keep that pressure up. Question number 25. Using the Q equation, calculate the energy needed to heat ice from -10 to 90 degrees Celsius. Guys, I apologize. I did not give you a mass. So don't worry about being able to do this, but make sure that you understand the Q equation looks like this, where Q is heat in joules, M is mass in grams, C is your specific heat, which is in joules over gram degrees Celsius, and then T is your change in temperature. So again, I apologize, I did not give you a mass. I would normally give you the specific heat value, which is 4.184 joules per gram degree Celsius, but I let you guys down on that one. I apologize. All right, number 26. What does STP stand for, and what are the conditions for STP? STP stands for standard temperature and pressure, and the conditions are if you have 1 mole of a gas at 273 degrees Kelvin at a standard pressure, which is our atmospheric pressure, then it will result in a volume for that gas. If you had 1 mole of that gas, would be 22.4 liters. Okay. I will not give you that value. If you want to memorize that value, it's probably not a bad idea. A lot of the stoichiometry problems that I give during the final exams are at STP. Just saying. Okay. However, if the conditions are not at STP, you may not use this 22.4 at all. You have to use PV equals nRT. 27. Use Boyle's law to calculate the volume of 10 liters of gas at 1 atmosphere when the pressure is decreased in pressure to 0.45. So we have a before and after. I'm going to be honest with you, I'm not going to give you Boyle's equation, Charles' equation, all those things. You have to know those, but you should be able to derive them from PV equals nRT, and I think in a later problem I actually do that. But again, P1, V1, where the number of moles, the ideal gas constant R, and temperature are unchanged, is equal to P2, V2, where the same thing, number of moles, ideal gas constant, and temperature are unchanged. Rearrange the variables so that you can get the variable that you're looking for all by itself and the other variables which we know together. Make sure your units cancel out, and that should, oops, I'm sorry, that is not liters. This should actually say atmosphere. My apologies. That should say atmosphere, so that the atmospheres can cancel out and we're left with liters. That's what happens when you copy and paste. I'm going to blame Microsoft Word. Thank goodness we're going to Google here shortly. Love it. 28, write the expression for using Dalton's law. Dalton's law deals with the law of partial pressures, where if you take multiple gases, put them together, since all gases, if they're not reactive, will exert their own pressure, because again, a gas is mostly made up of empty space. So if you have two gases put together, you're going to take that partial pressure of the one gas with the partial pressure of the other gas, put it together, and we have a total pressure. So this question is talking about the pressure of gas above water in a sealed container. So you have water vapor, you have, in this case, looks like hydrogen gas, put them together, and we get the total. And what this statement here, when the water levels are equal to each other, we had the lab where we had our water here, and you took your container, actually you'll do this in AP, and you'll move your container up and down until the water level, once you bubble a gas through that the levels inside and outside are the same. When the levels, water level inside and outside, are the same, that means that the gas that's in here is actually at atmospheric pressure. So then it's very easy to find out if we can measure the pressure using a barometer outside of the container, we can tell what the pressure is inside. All right, number 29. Number 29, what is the pressure of a dry gas that is collected over water at 10 degrees and 250 milliliter container? And it says the partial pressure of water is 1.2 kilopascals at a pressure of 1.2 atmospheres. I'll be honest with you, all it's asking for is what is the pressure of the dry gas. So we don't care about that, we don't care about that. Those are what we call distractors. What we do care about is right over here, where we have our partial pressure due to water, and then we have the pressure of the whole system. So in this case, we want to change one to the other. In other words, either atmospheres to kilopascals or kilopascals to atmospheres. And I think I just went ahead and changed them to kilopascals. Doesn't matter which one you do. It should still give you the same thing. In this case, it's 120 kilopascals. If that were atmospheres, it'd be a little over 1, because 101.325 kilopascals equals 1 atmosphere. Okay, so I'd say about 1.2-ish, maybe 1.18. Okay? If you were doing atmospheres. I didn't do both those calculations, sorry. Question number 30. Use Charles' law to calculate the volume of 5 liters of a gas that decreased in temperature from 80 to 10 degrees. Again, when we talk about Charles' law, it's a temperature-volume relationship. So as the temperature goes up, the volume goes up. As the temperature goes down, the volume goes down. Looking at this equation, it went from 80 degrees to 10 degrees. So as we should expect, starting off at 5 liters, we should go to 4. But as I carefully look at the calculation here, I have these two numbers mixed up. So we really should have 353 on the bottom. I apologize for that. And 283 Kelvin on top. But again, I must have, when I was writing it out on paper, calculated the 4 liters correctly, but wrote that incorrectly. So, lesson learned here. Make sure that we are, when we're putting in our values for our variables, not a bad idea that as you're going along here, to actually write out what these things are. So, like in this case here, we have V1, T1, T2, and that's why I had those two flipped, because I wasn't careful when I was typing. So be careful there. All right. 31. What is the molar volume of gas at STP? I think I did that earlier. 22.4 liters. Again, that value will not be given to you. You would have to know that on your own. 32, state Avogadro's principle. Avogadro's principle is the one that deals with as long as the temperature and the pressure remain the same, as you introduce more gas particles, the volume gets larger. If you allow those gas particles to escape, the volume gets smaller. Pretty simple. 33, using the ideal gas law equation, calculate the following. Recall that we must have our units the same as R. So if you're using R that has atmospheres, make sure you have atmosphere liter, mole Kelvin. If you're using the one with kilopascals, it's kilopascal liter per mole Kelvin. But we have to change our units to the same. So take a look at these answers. So on the first one, we had the moles, which is already good. Have to change the degrees Celsius to Kelvin. Have to change the milliliters to liters. And I did that in the problem. And I got, since it didn't ask for atmospheres or pressure, I typically use the atmosphere R value. And notice that I have the second part down here. I'm not a big fan of double division lines, so it just helps to minimize the chance of making errors by having multiple division lines. So take a peek at these other ones in number 33. And I'll kind of scroll slowly here. And if you need to, you can back up the video to take a peek at the answers. Okay. All right. And I'll scroll E up here. Number 34. Number 34. How many grams of sodium would be needed to react with 200 milliliters of chlorine at STP in the reaction? So again, step one, write a balanced equation. And I believe that was given to you, so you're welcome. So step one, write a balanced equation. Step two, take what was given. So in this case here, we had 200 milliliters of chlorine, and it's asking for how many grams of sodium. So I need to take this 200 milliliters of chlorine at STP, so I have my volume, I have my temperature, I have my pressure. Also, I know that if I'm at STP, 1 mole of any gas has a volume of 22.4 liters. So I want to take my volume and change it into liters and then use the conversion. So everything that you see here, that's step two. Step three, use the mole ratio. What that means is I started with chlorine, now I need to cancel the chlorine out to get to sodium. Not a limiting reactant problem because we only have one amount given to us. And then the last step, step four, change to the desired unit. In this case, the problem wants it in grams, so make sure you convert it to grams. (35). This is a stoichiometry and a limiting reactant problem. So I have carbon, oxygen. I also have 5 grams of carbon, 30 liters of oxygen. Doesn't matter which one you start with. I just so happen to pick the gas because it's easier for me to do the conversion from liters to moles that way. But again, you decide what you want to do there. So step one, write a balanced equation. Don't think that was given, so I have to write out the balanced equation again. If it ends in "-" or "-", it's a diatomic. Carbon is not "-" or "-", so carbon's all by itself. Oxygen, however, GEN, is diatomic. Put the two together, there's no balancing of charge, carbon dioxide, so hopefully you know that. So my limiting reactant step, I have to find out which one I'm going to run out of first, the 5 grams of carbon or the 30 liters of oxygen. I just chose the oxygen. So step one, write a balanced equation. Step two, take what was given, convert it into moles. Step three, use the mole ratio, get rid of what you started with. And step four, go back to the unit that the other thing is in. So it says it's 5 grams of carbon. So I'm not going to stop at moles. I want to go to the unit. In this case, my desired unit is grams. So in this case, I want to change it to grams, even though I started with liters. When I finish with my calculation, it says that I would, if I were to use all 30 liters of the oxygen, I would need at least 16.1 grams of carbon. I don't have 16.1 grams. I only have 5. Therefore, my limiting reactant must be the carbon. Very good. Because if you don't have enough to use all of the oxygen, then we're going to run out of carbon before we have a chance to do that. So take your limiting reactant, do the same thing. Change it into moles. then use your mole ratio, and then go back to the desired unit, because again, in this question, it wanted to know how many grams of carbon dioxide was going to be produced. So that works out well. Okay? All right, number 36. What determines whether a solute, liquid or solid, will dissolve in a solvent, a liquid? Again, like dissolves like. Polar compounds are dissolved in other polar compounds. Nonpolar compounds are only dissolved in nonpolar compounds. So if I paint with oil-based paint, I cannot rinse off my brush with water. I have to use an oil-based solvent. Gasoline, turpentine, paint thinner. Those are all good things that would work. Acetone would work. Okay? Those are all things that are not polar, non-polar. Okay, so like dissolves like. So if you're not sure, draw the Lewis structure and look at it. Define saturated, unsaturated, supersaturated. Unsaturated means that if I drop crystals into a liquid, those crystals, before they hit the bottom, will dissolve or dissociate. They'll break apart. It'll look like it's going away. If it's saturated, I drop the crystals into the liquid, those crystals should hit the bottom of the container. In other words, you'll see that crystal just fall to the bottom through the liquid, because that liquid can no longer dissolve any more of the solid. Supersaturated, if I have a liquid and I take a crystal and I drop it into the supersaturated solution, as soon as that crystal hits the liquid, the whole liquid turns into a solid. And I do have a video for that. 38. Calculate the molality of a solution containing 300 grams of calcium chloride dissolved in 400 grams of water. So we're looking for molality. Remember, molarity is big M, molality is little m. Difference between the two, molality is moles over kilograms, where molarity is moles over liters. Okay? So make sure you're reading that carefully. So in this case here, you have 400 grams of water. Convert the water always to kilograms. Whatever's not water, convert it to moles. Then take your value and plug it in and get your initial molality. However, since this is an ionic compound and that calcium chloride dissociates into 3 particles, we have a Van Hoff factor here. So we can't just say that the molality is this. We actually have to have a multiplier. So the true molality of this solution, once it's been placed into water, is 3 times what you may have calculated. So it's 20.3. 39 says calculate the mass of 75 grams of sodium hydroxide dissolved in 300 grams of water. You're not going to have to do a calculation where you figure out what the mass is dissolved in water, but I might ask you to calculate what is the percent of sodium in sodium hydroxide. That I expect you to be able to do. So if I had 1 mole of sodium hydroxide, then 22.99 grams of that 40.0 container of material is made up of sodium. Okay, so you find out the molar mass of the whole thing divided by the molar mass of the thing that we're looking for. And I think I had a problem like that on the previous problem there. But you will not find a question like that. 40, what happens at a vapor pressure of a solution? And let me see here if I can kind of scoot that up a little bit. I apologize for that. Number 40, sorry. Sorry, I had to do this because I can only put so many questions on the Smart notebook. So number 40, what happens at a vapor pressure of a solution when the amount of dissolved solute is increased? Anytime you add stuff to water, it actually elevates the temperature at which it boils at. So if you're raising the temperature at which a substance boils at, then the vapor pressure is actually going to be decreased, because if it has a higher boiling point, it has a lower vapor pressure associated with it. So if you're adding stuff, again stuff, mostly ionic compounds, but it could be molecular as well, it will lower the temperature, or I'm sorry, it will lower the amount of liquid that changes into a gas, because by adding that, it actually has a higher boiling point. All right, number 41 says the freezing point is lower and the boiling point is higher when it's compared to a solution of a pure solvent. So when we talk about, if I look at, say, I have pure water and I add salt to it, it will raise the temperature at which it boils at, and it will also lower the temperature at which it freezes at. So it actually moves away from that. Here's the main reason why, and we really didn't talk about it in class, but when you look at whatever you're adding to water, as long as it has a higher boiling point, like sodium chloride has a much higher boiling point than water, because it's a solid at room temperature. And also, it has a much lower freezing point because it's a solid at room temperature. Then that means that it will lower the temperature at which water will freeze at. That's why we sprinkle salt on the roads when there's ice on there, because in a sense it melts the ice, but what it really is doing is it's lowering the temperature at which water freezes at. Calculate the freezing point of a sodium chloride solution that has a water solvent of that has water as a solvent and 10 grams of sodium chloride dissolved in 75 grams of water. So again, always show the dissociation reaction first. So we want to find out what our Vant Hoff factor is. That's what this I is. So if I take 1 molecule of sodium chloride, I get 2 particles from that. Actually 2 ions, sodium and chlorine. And then what I'm going to do is I need to change my grams of my sodium chloride into moles, because again I need to plug it into the equation that is provided for you on the back of your periodic table, where the delta T, again the changing point of the temperature at which it freezes at. So we're going to lower the temperature at which it freezes at. Again, the I is a Van Hoff factor, the K sub F, that's your constant. This would be given to you as well on the back of the periodic table. And then we just found out our number of moles here. This is actually equal to 75 grams. So you have to convert the grams of water into kilograms of water. Plug all that in, and I get a delta T sub F, change in temperature of 8.49. What I do with that is I now take my value, which freezing point is 0, subtract that, because again, we need a lower freezing point, and that will give me my final answer of negative 8.49. 43. Identify the acid-base, conjugate base of the following reaction. So this one's a little bit different, but you have to look at the before and after. So HCO3, bicarbonate, has 1 hydrogen. Over here, carbonic acid has 2 hydrogens. So what that means is somewhere a hydrogen jumped on there to go from 1 to 2. Where'd that hydrogen come from? Right there. So in this case here, this is my acid, this is my base. Because again, we're looking at the before and after. Over here, you'll notice that there's no hydrogen with that chlorine. Yeah, it's a double replacement reaction. The sodium and the chloride are coming together. Not really, it's soluble. But this right here, to get it back, if I were taking H2CO3, it would have to get rid of a hydrogen. So in that case, this is my conjugate acid, or this is my conjugate base. 44, the range of pH for acidic solutions, approximately 0 to 7, or 1 to 7. For basic, 7 and up, so 7 to 14. Calculate the pH of a solution where the pOH is 4. So again, pH plus pOH. pH plus pOH equals 14.0. So you already know one of them. Subtract it from 14. 47. Calculate the pOH for a solution where the hydrogen concentration is at. So here's my hydroxide concentration. I can find that, and then to find the pOH, I didn't show it on here, I have to take the negative log of my hydrogen concentration, which I just found. Sorry, of my hydroxide concentration, which I just found. Boom. And so in this case here, negative log of 3.33 times 10 to the negative 10. That's going to be a number between 9 and 10. So negative log, negative. So 9.48. Okay, so equals 9.48. Now again, remember, always show your pH with 2 decimal places. Okay. All right, 49. In a titration, what is the concentration for the HCl if 20 milliliters of NaOH at 0.3 molar was needed to neutralize 50 milliliters of the hydrochloric? So here is my volume for the acid. Let's use a different color here. There's my molarity for the base and my volume for the base. So I'm solving for the molarity of the acid there. So rearrange to find that accordingly. 50 says, identify the element being oxidized and reduce the oxidizing agent, reducing agent. Okay, so we have to find out what the charges are to find out if something's being oxidized or reduced. So hydrogen, +1. We have nitrate here, NO3 with a -1 charge. We know that all oxygens have a -2 charge. We know that all oxygens have a -2 charge. Since there's 3 of them, they actually equal -6 total. If the whole thing equals -1, the whole NO3 equals -1, what that means is that this has to be a +5 charge. Okay? So nitrogen right here has a +5 charge. Talked about this earlier in the year. Over here, again, there's 2 oxygen, so that means that we have -2 times 2. Therefore, this nitrogen has a +4 charge. Going from +5 to +4 means it's getting more negative. Therefore, what that's going to indicate to us is that we are gaining an electron. So in this case here, the nitrogen that has a +5 charge gains an electron, so now it has a +4 charge. Anytime you see that electron right here, that means that it is gaining an electron and it's being reduced. Iodine, let's use a different color here. Iodine has no charge, but over here it's in this compound IO3. And IO3, let me erase this here. Okay. IO3 has a charge of -1 as well. We know that because there's 1 hydrogen there. So again, the oxygens, there are 3 of them. So total charge of -6 on the oxygen, the whole thing equals -1. Therefore, this iodine also has a +5 charge. But in this case, it went from no charge to a +5. Now, I'm not going to write out the whole equation, but I'm going to tell you that it is losing electrons. Okay, I'm not going to balance that out for it. So the iodine is losing electrons because it has them all here. And then the nitrogen is gaining electrons. So, who is oxidized? Let's do this correctly. So, iodine is oxidized. The nitrogen is reduced. And when we talk about agents, it allows the other thing to do what it needs to do. So, since iodine is oxidized, it's giving away electrons. Where are those electrons going? Well, right here. The nitrogen's grabbing them. So this is the reducing agent. And the reducing agent actually is in the molecule that allows that to occur. So in this case, I2 is the reducing agent. Okay. If the nitrogen is being reduced, what that means is it is taking on electrons that the other thing is losing. Therefore, this is the nitrogen, is the oxidizing agent, okay, or the thing has nitrogen in it. Therefore, the oxidizing agent is that whole compound there, HNO3. And ammonium nitrate is a really great oxidizer. It's actually used in some pretty powerful things, but we're not going to talk about that here. Okay? All right. Looks like the last question here. I don't know why I jumped from 50 to 54. I apologize for that. But the last thing here is having you to determine oxidation numbers, which was kind of important for up here. Determining the oxidation number or the charge on each of these elements. So KMNO, okay? So we want to find out how many we have. So we have 4 oxygens. As we stated, the oxidation number for that is always going to be -2. So 8 times -2 is -8. Potassium, group 1A. So if we were looking at our periodic table here, potassium's right here in group 1A, so it has a +1 charge. Therefore, we have a, how many do we have? Only 1, so we have 1 potassium with a +1 charge. Therefore, that equals +1. And since we know that the whole compound has a total charge of 0, then we must have a +7 charge for our manganese because we only have 1 manganese as well. So your oxidation numbers are actually these right here. So that's how I got my +1, +7, and -2. Let's take a look at the next one. C2O4 or oxalate, not 1 or 10 polys. So oxalate, C2O4, -2. There's carbon, 2 of those, and oxygen, 4 of those. Again, oxygen's really easy, -2, so -8. However, in this case, the whole compound has a -2 charge, which makes that kind of nice. So we need to make sure that whatever number we get here has to equal -2. So if I were to go +6, okay, I can see that. And in that case here, that gives me +6 divided by 2 gives me a +3 charge. Okay. All right. Hope this video was helpful. Again, take a look at the first video from the first review sheet. That has a lot more math on this. This one was more concept based. And I hope this video was helpful.